Welcome back to my channel, where you, me, and my houseplants are going to have some fun doing math. Today, we are looking at limits once again. So to remind you, we say that the limit of some function f of x as x goes to a is equal to b if the limit as x goes to a from the left is equal to b and the limit as x goes to a from the right is equal to b. So in today's video, we're going to look at actually evaluating some limits. So our first example says, find the limit of this function f of x equals x squared minus x minus 2 as x approaches 2. So here we have the graph y equals f of x, and we're interested in looking at the limit of this function as x goes to 2. So we're going to start by looking at the limit as x goes to 2 from the left. And so what I mean by that is we're looking at values of x less than 2 but approaching 2. So we might start with, say, 0. So when x is 0, my function is way down here at minus 2. If x is 1, then my function is over here. It's still at minus 2, but we're on our way up now. If I look at 1.5, well, my function is increasing, and the closer I get to my x values being equal to 2, the closer I'm getting to my function being equal to 0. So we'll say that the limit of this function as x goes to 2 from the left is going to be equal to 0. Next, I'm going to look at the limit from the right-hand side. So the limit of the function as x goes to 2 from the right, I'll start by looking at values larger than 2. So maybe I'll start with x equals 4. Well, we can see that our graph is off the picture here. We can't even see our graph when x is equal to 4. It's somewhere up here, and it's decreasing. So if I take, say, x equals 3, then my function is coming down. As I take, say, 2.5, my function is decreasing in this direction that I'm interested in as I go towards 2. As I take x values closer and closer to 2, my function is getting closer and closer to 0 again. And so we say that the limit of f of x as x goes to 2 from the right is equal to 0. And so we can say that the limit of f of x as x goes to 2, because it's equal to 0 from the left-hand side and it's equal to 0 from the right-hand side, you say that the limit is equal to 0. Notice something interesting happening here. We were looking at values of x very near 2, but we weren't actually talking about the function at 2. So the limit specifically is looking at the behavior of the function near the value. But one thing we notice here, if I plug in x is equal to 2, I'll have 2 squared minus 2 because my function was x squared minus x minus 2. And that gives me 4 minus 4, which is 0, which is actually what our limit was. In this example, we actually have that the limit of f of x as x goes to 2 is equal to the function at 2. So we could have just evaluated our function here. And that brings us to an important theorem. So this theorem says that if f is either a polynomial or a rational function, and a is in the domain of f, that's an important note, a has to be in the domain of f, then we can say that the limit of f of x as x goes to a is equal to f of a. So that means if we have an example like the one we just looked at, we don't actually need to talk about approaching that value. We can just plug it right in. Naturally, a question comes up. What if a is not in the domain of our function? What do we do then? Let's look at an example. So here we have another function. It looks similar to the one we were just looking at, x squared minus x minus 2, all over x minus 2. So the difference here is this is a rational function, meaning it looks like a fraction. What is the domain of our function? So whenever you're given a rational function, you want to think, what is the domain of this function? So remember, the domain is a set of all possible inputs. In our example, we want to look at what can we put into our function and what can't we put into our function. So if you look at this rational function, what kind of value would give you something bad happening? So it's often easier to point out what we can't put in a function as opposed to listing all the things we could put into a function. So in this case, we want to avoid division by 0. Because we have a rational function, we always want to be aware of our denominator and make sure we're not dividing by 0, because that is a big no-no. So in set notation, we will say our domain is all of the x values in the reals, meaning all of the real numbers, so fractions and decimals and all of those numbers are allowed, such that x minus 2 is not equal to 0, because we don't want our denominator to be equal to 0. So another way we might write that is that the domain is x in the real numbers, where x is not equal to 2. You may also write it as an interval, which says I can take any number from minus infinity to 2, but I can't take 2, and I can take any number from 2 to positive infinity, but once again, I can't choose 2. So we've set all of the real numbers except for that one value. Naturally, we become interested in what's happening at 2. So I know I can't plug the value of 2 in to my function, but I still want to know kind of what's going on there. That's where the interesting things are going to happen. And so we can start by looking at the limit. So we'll look at the limit numerically first, meaning we'll actually plug in values approaching 2 from the left and approaching 2 from the right. So if I look at values from the left, this table will be the values on my left-hand side and my right-hand side. If I plug in a value like 1, I have 1 squared minus 1 minus 2 all over 1 minus 2, which is minus 2 over minus 1, which is positive 2. Almost ran out of room there. So I've gone ahead and evaluated these other values. So f of 1.5 is going to give me 2.5. And as I approach x equals 2 from the left, I see that the y values that are coming out of my function are getting closer and closer to 3. Let's see what happens if we go from the right-hand side. We get the same value. If I plug in 3, f of 3 gives me 4. Coming in from the right-hand side, I'll choose a value smaller than 3 for my x value, so say 2.5. And I notice that the closer my x value gets to 2, the closer that my function is getting to 3. And so numerically, I can estimate that the limit of x squared minus x minus 2 all over x minus 2 as x goes to 2 is going to give me 3. But sometimes we don't want to numerically set up a table and find all those values. That's a lot of calculation. We'd also like to prove algebraically that this is in fact what's happening, that something crazy doesn't happen when we get too close to 2. So how can we show that? So we'll start with the limit from the left-hand side. So as x goes to 2 from the left, we know we can't apply that theorem we just used because 2 is not in the domain. So instead, I'm going to try and simplify my expression. So this is a trick that we'll use again and again when we're evaluating limits. So notice that the numerator of my rational function can be factored. I'm looking for two numbers that when I multiply them together, I get minus 2, and when I add them, I get minus 1. So what would those values be? Well, I know 2 times 1 is the only thing I can multiply, or the only whole numbers I can multiply together to give me 2. And so because they need to add to be minus 1, I need -2 and +1. Now notice what's happened here. I have an x minus 2 in the top, a factor of the top is x minus 2, and I have x minus 2 in the denominator. And so I can cancel those factors out of the top and the bottom. Now notice, an important thing to notice here, if I was doing this to just a function, that would change its domain. Because the function x plus 1 and the function that we're looking at are two different functions with two different domains. But because I'm only looking at the limit, I'm only looking at values near x equals 2, it doesn't matter that I've kind of altered the domain because the behavior near x equals 2 is going to be the same. And so I write that the limit is still equal. I get the limit as x goes to 2 from the left of x plus 1. Well, now x plus 1, there's no hole in the domain. The domain of x plus 1 is all the real numbers. And so I've gone back to almost the example I had in the first example. I have a polynomial. I can plug 2 into that polynomial, and so I will. And I get that that is equal to 2 plus 1, which is 3. So the limit of this function as x goes to 2 from the left is equal to 3. We've proved it algebraically. And you can do the same thing to prove the right-hand side by following the same methods. Because notice, nothing actually relied on the fact that I was taking values from the left. Sometimes it will. But in this example, it will be the exact same argument. So I'll leave that for you to do. And so we have two interesting results here. The first one is that the function x squared minus x minus 2 all over x minus 2, the function that we're interested in, behaves the same way as the function x plus 1 anywhere that x is not equal to 2. So take a second and think about what would that mean for the graph of these functions. How would they compare? Well, if they're the same everywhere except for x equals 2, then their graphs are actually going to look the same. The only difference will be the one we're dealing with, the one we're playing around with, has a hole at x equals 2, and x plus 1 does not. So the difference between them is their domain, but otherwise they're the same. And so that's why we can use the function x plus 1 to talk about the behaviors of this more complicated function that we're actually interested in. And so finally, our other result is what we were trying to show, which is that the limit of this function as x goes to 2 is equal to 3. We have now proved it, we showed it numerically, and we proved it algebraically. The last thing we're going to do here is look at a strategy for approaching these types of problems. So if you're given a rational function or a polynomial, and a is in your domain, so the value that you're approaching is in the domain of the function, then you can go ahead and evaluate your function without doing any more work. If a is not in the domain of your function f, then you have a bit more work to do. Your first step is going to be to try to simplify the expression of your function so that you get a new function whose domain does contain a. And once you've done that, you're back to step 1. You can plug it in and evaluate it, and you are done. In further videos, we'll look at other techniques for simplifying more complicated expressions. Until then, I've left some exercises for you to try, so go ahead and look at those. Remember, first ask yourself, can I plug this value right in? And if not, how can I simplify the expression? Thank you so much for watching. I hope you enjoyed this video, and I will see you next time.